Good day to you all. I am going to start today's topic, which is multi-component fractionator design. Well, you can call it a fractionator or a fractionation system, whatever it is. To start with, we definitely have to remember that we have covered the binary system distillation design already. Now, the first thing that we have in our mind, there are two approaches to multi-component design, which is also certainly applicable to binary system designs as well. The first is a rigorous approach. That means, if you are talking about a particular distillation tray, if you are talking about a particular distillation tray here, from where a vapor leaves and a liquid falls off, this liquid and this vapor are in equilibrium. They are in equilibrium. So, that is a fundamental consideration here. In case of the rigorous approach, what you have, there are equations which will be telling you that around every tray, the enthalpy coming in and the enthalpy going out should match. The enthalpy comes through the vapor approaching this envelope and as well as the liquid approaching this envelope, and the vapor leaving is from the top of this tray itself and the liquid falling off the tray here. So, there has to be a balance of enthalpy of coming in, which is coming in and going out. Exactly in the same way, in the same envelope, there should be a balance of every component that comes in and go out. That means, we first start with an equilibrium approach, an ideal tray. We know that ideal tray assumes equilibrium, which is not possible. So, the concept of tray efficiency has been introduced to you, and you already have used and employed it in case of binary distillation. The definition of tray efficiency, particularly the Murphy tray efficiency, is simple. It is basically the actual concentration in vapor composition achieved on a tray divided by the maximum it could achieved. That means, the difference is due to non-approach to the equilibrium on a real tray. Now, this is about the rigorous approach, but we understand that this is going to be really rigorous. That means, it involves lot of calculations, lot of data and a good amount of mathematical manipulation as well. So, there are people who thought over it and came up with a shortcut approach. In fact, what we are going to tell you today is a one shortcut method, which is typically known as Fensky-Underwood-Gilliland method, but there are other methods as well. Obviously, such systems are based on similarities with binary system. That means, in a binary system, we know there are two components which are to be separated. So, the first step in the shortcut approach is to identify two components in this system. The separation between these two attains the goal of the separation of the multi-component system. So, the first step always will start with identifying the light and the heavy key components, and these are the light and the heavy key. Exactly what I have said, it is the separation of the light and heavy key represents the meeting separation target of the distillation process being designed. We very quickly recapitulate. We recapitulate the definition of relative volatility in terms of the saturation pressure at a particular temperature, in terms of the mole fractions y and x, and also in terms of the distribution coefficient k I and k j. So, alpha I j expression is what you see here displayed. The Valley xy relationship is also given by yi equals alpha x divided by 1 plus x into alpha minus 1. Perfect. So, if I know my alpha, if I know my x values, the corresponding y values can be found out. This is regarding binary, mind it. Then we also appreciate that the top and the column bottom temperatures are different, because the top temperature contains lighter components, the bottom temperature has got a higher proportion of heavier components. So, naturally the top temperature is less than the bottom. This makes a difference between the alpha value at the top and alpha value at the bottom, and for design the convention is used to use a geometric mean of the alpha at the top and alpha at the bottom as shown here. In order to appreciate multi-component design, we start with a design problem. Say the feed stream contains 3 components. The first is benzene, the second is toluene and orthoxylene in order of decreasing volatility. I have written here the feed contains 0.35 mole fraction of benzene, 0.25 mole fraction of toluene and 0.4 mole fraction of orthoxylene. The target of separation tells us that minimum 85% of the benzene has to be recovered, and the recovered benzene has to have minimum 95% benzene purity. So, what we could decide is definitely my mole fraction of the distillates are going to be 0.95 for benzene. I decide that I am not going to send any orthoxylene up. So, naturally the rest amount is toluene and there is no orthoxylene. So, its mole fraction is here is 0, and the problem is design the fractionator. So, we definitely what we find is we have benzene, we have toluene, we have orthoxylene, and if I look here the B and the D here, benzene is available at the distillate, toluene is available at the distillate. We recover only 85% of the benzene. So, the rest amount of benzene will be present in your bottoms. Naturally, if benzene is present in the bottoms, the heavier ones will be available there too. So, what we find here is that the lightest component in the distillate, the lightest component in this is basically the lightest component in bottoms. And what is it called? It is called the light key. And what is this? This is basically the heaviest component in D. What is that? This is called the heavy key, and that is the convention. So, if we can achieve a separation between benzene and toluene, which are basically the light key and heavy key, the separation target will be fulfilled. That means, we will be sending, we will have common components between the bottoms and the distillate, but our target will be fulfilled in this way. Let us look at fixing this light and heavy components, heavy key components in slightly more details. To start with, in a formal way, we understand and appreciate that all components may not be present in the distillate as well as the bottom product, that we have seen already. Usually, only a few are common. The separation target is specified by limiting the concentration in D or in B, or in both at times. In simple words, among the components common in D, light key is the lightest in B and heavy key is the heaviest in the distillate. We go for an example, another example in fact. We talk about a column in which the target is to separate LPG, mostly C3 and C4 hydrocarbons, from a mixture of naphtha which contains C2 to C9 hydrocarbons. That means, it is an unstabilized naphtha feed, and during separation one thing is sure, if I am going to use this separation to be carried out in a fractionator, C2 is the lightest, and possibly that is not going to condense there, because if I have to condense C2, I either require a very high pressure column or I need a cryogenic column. So, quite likely it will be so that I will be losing the ethane as vapor from my reflux drum. You know what the reflux drum is already, and possibly along with it I will be losing certain amount of C3 as well, which is propane. Now, we have two cases here. We move to the next slide here, in fact have a look at a table here and see the composition of the feed being listed here starts with ethane and ends with C9. It is in the order of decreasing volatility, and the composition is also known. The first thing you will see, we are talking about this particular case, that means the case 1, which I have referred to in my last slide. And here what we have is, we decide that my top product is definitely not going to contain any NC5. So, basically my top product is going to contain C2H6, C3H8, ICH10, NCH4, I5H12 and NC12. That means these components. The bottom product will definitely contain the rest. That means it will start from this one and continue up to my C9 component. So, in this particular case, we note here very clearly that the common components are NC4H10 and IC5H12. So, what will be the light key in this case? The light key is what? The light key is the lightest in the bottom product. So, this is definitely going to be my light key, and obviously the heavy key is the heaviest component in my distillate. So, this is going to be my heavy key. Now, the same separation, that means with the same feed, the top product being LPG again, which is expected to be primarily C3 and C4, I consider it a different case. What do I have here? I have here, I am going to accommodate certain amount of NC5 in this also. So, can I say, or can you appreciate at this particular point, that the LPG, which is a distillate stream here, in the left case or the case 1 is not going to contain any NC5, in the right side case or the case 2 it is going to contain this. So, your LPG is going to be purer in the first case and is to be relatively impure in the second case. Quite naturally, you have an extra yield of LPG volume of production in the second case. Now, obviously again my distillate again will be containing these and up to my NC5H12. And quite naturally what we have is, we also have these components at the bottom. Now, instead of just two common components between the D and the B, we have 3 here. Now, we go and identify the light and the heavy key. The light key is supposed to be this. So, this is going to be my light key. Why it is a light key? Because it is the lightest component in my bottoms. This is going to be my heavy key, because this is in this case is going to be the heaviest component in my distillate. Now, apart from the light and the heavy key, you have at least one component which is in between, which is present in both. So, this is called a split key, which has volatility between the light and the heavy and is present. So, naturally all key components will be present in both distillate as well as the bottoms. The light key and the heavy key will be the extreme ones, and the split key will be present in both as well. Normally, the split key is considered to be distributed between the distillate and the bottoms according to their volatility, and this we will see later on when we come to the calculations. The technique which I have mentioned right at the beginning is the Fensky-Underwood-Gilliland method. You already have understood and you appreciate that we talked about a lot about the minimum number of ideal stages required for separation. We did so. So, that we designate by S subscript n. We also have talked about the minimum reflux ratio for the targeted separation, designated by R m. Sometimes we say R m, sometimes we say R minimum, does not matter. The Gilliland equation definitely is the most important equation at the end. That means which definitely is going to give us the actual number of theoretical stages, ideal stages required for the separation at a particular reflux ratio of R, which is definitely more than R minimum, because R minimum is the minimum required. Your actual operating reflux R has to be higher than R minimum. There is one more thing which is also there that we will see later on, that is how to split the total number of stages, which is basically S, which is found out from the Gilliland equation, into the stages above the feed tray and the stages below the feed tray. At the same time, obviously, this is going to tell us the location of the feed tray as well. Now, we look at the Fensky equation. We have the case of a total condenser given here. Here it says Sm, which is S minimum, the number of minimum theoretical stages required for the separation, is equal to log of something something divided by log of alpha. Quite naturally, the number of stages required would depend on the relative volatility. It will also depend on the concentration required in the top and the bottom products of the light and the heavy key. So, this is expectedly an known expression or something like this. Now, if you look at the distillation system, we will find there is one vapor liquid contacting which is happening in your reboiler. So, if you have Sm number of stages, your number of stage of contact that you have to provide inside your tray, inside your column or tower, is less than Sm by 1. That means, basically Nm is equal to Sm minus 1, which is again reflected here in the same equation as an additional term. This was a case of total condenser. We can have a partial condenser also. In a partial condenser, it provides one more vapor liquid contacting stage. So, what happens is the number of trays to be provided inside the column or tower has to be further reduced by 1, is diminished further by 1. Now, in a distillation column, typically you may or may not think that rather what happens is the contacting in on the feed tray is not usually very proper. You have a distribution problem, you have condensation of some vapor component coming in contact with feed and such things. So, what happens is, if you do not take credit for this, you have to increase the number of stages which is required in your column by 1 more. So, definitely in that case you will be adding 1 more to the Nm value that you have finally arrived so far. So, one thing is true, up to this particular point we have decided on my Nm, or the minimum number of ideal stages or ideal trays that I have to produce that I have to provide inside my tower or the column itself. What is the next thing to be done? We need to find out the Rm, which is the minimum reflux required for the separation. Now, you will notice one thing, if you look at you definitely remember the binary system. How did we locate the point of minimum reflux for a particular separation? There we required the composition of the feed as well, because it was a point where on the equilibrium line, where the two operating lines, stripping section operating line and the rectification of section operating line, they came and met. So, quite naturally the expression of Rm, which is given by the under root equation, would contain parameters related to the feed and parameters related to the distillate as well, and certainly the equilibrium will be represented by the alpha term. So, we can appreciate very well why these terms appear in the expression of Rm. And at this particular stage, all these parameters are known, and it is possible for you to estimate an Rm in the problem. This is a case where the Rm is found when the feed is at its dew point. We also know that the feed line and the two operating lines in case of the binary met on the equilibrium line, and that depended on the value of Q or the slope of the feed line or Q line or F line, whatever you may call. So, quite naturally your Rm should also be a function of Q. So, in this specific case Q is equal to 0, and quite naturally you need not have a value of Q here. In the previous case the Q value was 1, which was put here, and you had an expression, explicit expression for Rm in the previous case where the feed was at its bubble point, and in this case what you have is the explicit expression of Rm with the feed at its dew point, which is vapor feed. When it is a mixture, the expression is rather complicated and you cannot have an explicit expression in Rm, but however, there is a relationship which can be solved by trial and error. If I know my Q, if I know my X values, if I know my alpha by trial, we can solve this and find out my Rm. So far what we have found out is, we have found out number of theoretical stages that we have to provide in my tower, within my tower itself. We also have found out for this particular separation extent what is the required minimum reflux under a particular fit condition with Q 0, 1 or some other value of Q. The next thing is, we again have something very similar to what we have done earlier. We had assumed a particular value of R by R minimum, and we had a procedure based on the construction of those triangular steps, and we found out the number of theoretical stages required for the separation. In fact, Gilliland gave us a correlation in the graphical form originally, whose mathematical form is here. This is the mathematical form, and this basically has been found out empirically, and it relates the minimum number of theoretical stages Sm to the real number of stages corresponding to R. That means, S corresponds to R reflux ratio and Sf corresponds to Rm, the other minimum reflux ratio, and this is the expression. Since we already have found out Sm, we already have found out Sm, it is Rm. So, definitely it is possible for us to know the value of S. Up to this is fine. That means, we know the total number of theoretical stages required. From this we know we will be subtracting and adding 1 for different reasons, for the reboiler, condenser, partial condenser, taking credit for feed tray or not, and we definitely will be knowing the number of trays required in total for the desired separation within the column itself. Now, quite naturally, if I have to ask for the column design finally, I have to specify the location of the feed. That means, the number of trays which appear in the stripping section and the number of trays that appear in the rectification section. This is done, this can be done in two ways. The first thing is an approach based on the Fensky equation. The Fensky equation considers the rectification of the stripping section as independent columns. That means, what you had is a feed, from the top you had a distillate, from the bottoms you have B. So, what you considered here is your column 1, this is a column 2. That means, for column 1 the top product is D, the feed composition is XF. For column 2 the top product, the bottom product composition in the column 1 is XF, and in case of column 2 the top product is XF and the bottom product is B. Now, based on this consideration, if we look at the number of theoretical stages required, the minimum number of theoretical stages required, the ratio of those two in the rectification section, which is column 1, and the stripping section, which is column 2, we have an expression like this. Here you will note that we are using the values of the composition of the feed quite naturally. This is definitely valid at a composition of minimum reflux, because that is based on the Fensky equation, which is valid for the minimum reflux, which is valid for minimum number of stage or total reflux condition. I made a mistake. I should have said for Fensky equation what is valid is the total reflux or the minimum number of theoretical stage conditions, Sm. We assume that the ratio is same. So, what we do next is based on this above ratio, we split n total, and after we have done that, we find out the number of rectification stages to be provided inside the column, divide it by the overall efficiency and find it out by after rounding off. Exactly the same thing we do for the number of theoretical stages to be offered for the actual separation, when the actual separation has got an overall efficiency of eta 0 to be this, and this is found out by rounding off to the next higher value. In case we have a large variation of relative volatility across the column, we do not have the previous expression, we have a modified expression which looks like this. Sometimes the approach based on Fensky equation does not give us the desired realistic result. In such case, an alternative equation proposed by Cartwright is used, which is again defined the same way. It involves the composition of the bottoms, the composition of the top, the feed composition in terms of the light and the heavy key, and also the yield of the bottom and the distillate streams. So, we look at if we can say now we have an overview of the multi-component distillation, and it is time that we have a look at the example design problem once more. The feed stream, I just repeat the problem here. The feed stream benzene, toluene and orthoxylene has got composition mole fractions of 0.35, 0.25 and 0.4. Minimum 85% of the benzene to be recovered with a minimum purity of 95%, and we have decided that my distillate composition is going to component no amount of orthoxylene. So, the composition is 0.95, 0.05 and 0, and a fractionator has to be decided. This is the full statement. That means, it is in fact a realistic problem with a feed rate of 20 meter cube per hour, and the same thing is given here. Only thing, this 75 is wrongly written here, it should have been 85%. And we are going for a quick design now. We know the feed composition, we know the molecular weights. So, what we find that my feed is 188.9 kilomole per hour. We simply have found out the composition of the distillate, and we have found the ones here. In fact, I will just make one more correction here, that this is not 85, this is worked out based on 75%. 85% is the problem which was given in the first instant right at the beginning of this particular lecture. Now, we know the distillate composition which is here, the quantity of is also known, and this is 0.95, 0.05 and 0, and by balance the composition at the bottom is also known, which is this much of benzene, this much of toluene and this much of this. The corresponding XP values are also given here. Basically, to conclude, let us have a look at the steps required to complete the problem here. The first thing is definitely finding out the light key and the heavy key that we have already said. My light key in this particular case is going to be my benzene, and my heavy key in this case is toluene, because and it is a case of adjacent key, because they appear in the same sequence one after another in the order of volatility. The first step after this should be deciding the accumulator temperature based on the coolant temperature which is used in the condenser, because the condenser outlet is going to have the temperature which is there in your accumulator, and there usually has to be a temperature gradient of anything between 10 to 20 degrees centigrade for the driving force to remain in your condenser. So, typically, so if you are using a cooling water arrive available at 33 and returned at around 45, your expected accumulator temperature is going to be something around 53, 54, 55 or so, or it could be slightly higher even. The next is finding the accumulator pressure, which is simple. Rather, we all know that the distillate is at its bubble pressure at the accumulator temperature within the accumulator itself. We know the distillate composition, so we find out the accumulator pressure by evaluating the bubble pressure of the distillate. Next, what we do is we are required to find out the column top pressure. The column top has to be at a slightly higher pressure, because the vapor has to flow from the column top through the overhead lines for vapor, go to the condenser and finally come out of the condenser as in the condensed form. Typically, the pressure drop will be of the order of around 0.3, 0.4 kg per cm square, which is added to the accumulator pressure in order to have an estimate of the column top pressure. The column top temperature is nothing but the dew point of the distillate at the column top pressure. We know the column top pressure, we just found it out. So, what we do is we find the dew point of the composition D at this pressure, and we note this as the column top temperature. We need to have initially a rough estimate of the column bottom pressure itself now. Suppose we decide that we are going to use, we expect around 18 to 20 trays in this type of separations. We consider roughly about 50 millimeter of water column per tray drop, add this drop to the column top pressure, and we have an estimate of the column bottom pressure itself. Now, the column bottom temperature is basically the bubble point temperature of B at the column bottom pressure. So, what we know now is basically the entire column profile of temperature and pressure. We know the relative volatility at the top and the bottom condition. We can use the design relative volatility estimate as the geometric mean of the column top and the column bottom relative volatilities between the light key and the heavy key. Obviously, once we have configured our column, the steps are simple. Using the formulae which has already been told to you, we evaluate Nm as per the Fensky equation, after definitely correcting for the +1 and minus that we have talked about earlier. We estimate the Rm from the underdrift equation, which is the minimum reflux required for the separation. We decide on an R by R minimum value above 1, maybe 1.1 or so, and find out the R corresponding to that particular R by R minimum of 1.1 maybe as a first trial. We find out the N total required, that is the total number of trays actually required as per the Gilliland equation, and the efficiency assuming around 0.7. We split this N total to the number in the rectification section and the stripping section, and we report the results. So, basically this is going to be the way we approach a distillation column problem which has got multiple components. We have considered only 3 components here, but there could be several, but the approach is similar because it is based on the similarity with the binary, just only the light key and the heavy key are identified and are worked upon. I think with this I will conclude the topic on design of fractionators, the multi-component fractionators. The next topic to be taken up will be batch distillation. Thank you.